Hello everyone, welcome back. So, we are in the last week of our course and we have basically solved simple problems, understood how CFD works for let us say gas dynamics problems. We looked at the shock tube problem, we made the geometry, the mesh around that, we solved it using finite difference. Okay, we looked at different schemes, different boundary conditions. We also looked at how the finite volume works if you want to let us say put in unstructured grid there, right. So, but that is just one problem of the shock tube. There are problems in nature or in engineering applications which are much more complex than what we have studied, right. The geometry may be very complicated. Let us say if you want to simulate a scramjet or if you want to simulate an aircraft basically at Mach number of 0.8 something like that, okay, or an aircraft where the flaps and slats all are deployed, the surfaces are quite complicated, the geometry is quite complicated in those cases. Okay, so solving those problems require you good understanding of the CFD, and at the same time you need a code which is basically well validated and it is robust and works for different kind of scenarios. Because let us say if you want to simulate flow behind an aircraft, okay, so there will be some regions, even if the incoming flow is at very high Mach number, there will be some regions where the flow may be separated and the Mach number will go to very small value. Okay, so the let us say the Mach number goes to 0.1 from 0.3. So, there the region is almost incompressible. So, if you are using the same solver from the beginning to the end, you have to have special consideration so that the solutions do not blow up, right. So, what people do in most of the cases that they use some well-weighted solvers. For example, some quite popular solvers are let us say ANSYS Fluent or ANSYS CFX, then we have COMSOL, okay, and then are basically there are solvers like Cascade, okay, solvers from Cradle Science. So, these are basically the commercial solvers, okay. On we also have like solver several open source solvers which are also coming up, and they have made a good name. For example, OpenFOAM is one of the solvers which is quite popular and many of you might be using that solver, okay, it is an open source solver, okay. And then we have uh, also solvers which works on basically the higher order problem. For example, XCompact 3D is one of the solvers, right. So, which you can use for solving high, I mean schemes, use higher order schemes in those problems, right. So, the question is like how do you employ such solvers? If you want, you can go ahead and develop your own solver also, right, but that requires quite a bit of effort if you want to solve a quite complicated problem, but it is not impossible, okay, if you are dedicated. And I mean there are some very nice AI based tools which can help you in writing the or giving you the basic structure of the code which you can modify, but it really need a very good experience in CFD for you for the code to work. Okay, so what we will do in the next few classes in the last week is that we first look at the some of the practical considerations in basically using a code. Okay, it can be a open source or a commercial code, or even if you are developing a code, these considerations will be very useful, right. And then we will also solve some problems in this week. There are a couple of things that we have not discussed in this course because of the lack of time. For example, we have not discussed about the turbulent flows. Even for the viscous flows, we have discussed not in great detail. The most of the discussion that we had in this particular course were on inviscid problems, right. So, we will do in the next few lectures, we will look at these complexities and then we will briefly discuss let us say what happens if the flow is turbulent, okay. What happens when the flow is viscous, what about the shock modular interactions, okay, and finally, how you can use the solver to solve these problems, right. So, let me start. Okay, so yeah, so this is the basically steps of CFD as we have discussed earlier. So, first thing is the pre-processing. Let us say if you want to simulate flow in a nozzle or something like this, okay, which is like this. So, this is your geometry, okay, and then you would be basically making a mesh around it. So, you will have boundaries there, and then you will have mesh going everywhere. Okay. So, this will be your, so this will be kind of mesh that you can make. You can have your own grid generator. There are elliptic grid generators or hyperbolic grid generators, or what you can do, you can use grid generators like ICMCFD or pointwise grid gen, grid pro. There are several commercial and open source grid generators as well, which can give you very nice grid. So, what we need to take care is that grid is orthogonal near the boundary as much as possible. The aspect ratio should not be very high, the skewness should not be very big. Okay, these are some of the mesh quality checks that you do. Okay. Even in open form, you have block mesh, snappy hex mesh kind of mesh generation tools, right. So, so these things, the what you see in the red are basically the boundaries. So, these you have to use the boundary conditions here, okay, everywhere on the left, on the right, and all those things. So, you might have the pressure here, okay, total pressure, maybe the back pressure here, depending on whether it is over expanded or under expanded nozzle. So, you have to accordingly adjust the back pressure. This might be the wall, okay, on both the sides. It may be 3-dimensional configuration, or you may think of making an axisymmetry configuration. Then you have to make an axisymmetry here, or you can try to simulate a wedge kind of configuration, right. So, this is an example of internal flow. This is very similar to, for example, what we had in the short sock tube. So, you had something on the left, okay, which was basically some pressure and density, and something on the right, okay. And if you want to solve it, let us say you want to do it in 2D, this will be like this. If you want to do 3D, it will be like this, and of course, 1D you can write your own code and do that. So, I would strongly encourage you to basically write at least one 1D code, okay, to solve simple problems like short sock tube. Okay. You can use your favorite flux schemes and try solving it. This will give you confidence that, okay, you understand what are the nuances of CFD. Okay. Even if you want to use like say OpenFOAM or any other solver for high dimensional problems, complex problem, that is fine, but the steps that we have, for example, how to make a grid, okay, how to distribute the points, then how to reconstruct, how to calculate the flux at the interface, okay, how to time march it, how to apply the boundary conditions, everything will become clear to you when you even write a 1D problem and solve simple problems like short sock tube, etc. Okay. So, if you are doing, let us say, external flow problem, let us say you want to do flow over an aerofoil or a wing, okay, then you only know that the flow is happening on this. You have to decide that how far you want to keep the boundary. Okay. So, what should be this distance, or what should be this distance, or what should be this distance, and so on and so forth. Okay. That is your choice, and if you are keeping it very close, okay, then what will happen, that the waves will get reflected from this side, okay, and it will basically corrupt the flow near this region where you are interested. It will not give you the correct lift and drag or any other flow feature that you would like. If you keep it very large, then your computational cost is going to increase exponentially, right. So, it is a balance. If you, in fact, when we discuss about LES or DNS, which are advanced simulation tools or simulation methodology, you want to make it as small as possible. At the same time, you have to use the boundary conditions intelligently, so that there are no waves coming and corrupting the solution near the aerofoil, right. So, so you have to, if you are getting a geometry, you have to clean up the geometry, make the external boundary how far you want to keep, okay, and then apply the boundary conditions here. If you have a periodic boundary, let us say you are doing flow over a turbine that we have been discussing, okay, then you have one turbine on the top and one turbine at the bottom. So, what is the distance between these two? This should be the periodic boundaries, okay, this one and this one, okay, this one and this one, and so on and so forth. And then you have inlet and outlet. So, all the boundary conditions that you have studied will basically come into play here. So, after you have done pre-processing, then what you need to do is you need to set up a solver. Okay. So, first of all, you have to decide what kind of equation you are going to use, whether it is incompressible, compressible, whether it is steady or unsteady, okay, whether it is laminar or turbulent. So, depending on your choice and your simulation technique, your equation may change. Okay, what kind of numerical scheme, okay, whether you want to use rho, whether you want to use HLL, HLLC, if it is compressible, if it is incompressible, there are schemes like piezo and AUSM, AUSM plus, not AUSM. AUSM and AUSM plus are basically compressor solvers. You have piezo and simple, simpler, etc. Then what kind of model you want to use, whether the fluid is Newtonian or non-Newtonian, whether its flow is laminar or turbulent. If there is a reacting flow, what is, if there is any combustion happening, then you have to use the combustion model also. So, you have to put these kind of models, put right boundary conditions. So, you have the boundary, okay. I discussed, like, let us say this is a flow over a turbine blade, okay. So, this is a boundary. Now, here you can apply the pressure inlet or you can apply the velocity inlet, okay. Here you can apply pressure outlet or you may apply non-reflecting boundary condition. So, that is your even if you have physically made this boundary, what should be your boundary condition? So, that is a very important question, okay, which can give you the correct flow, right. So, that you have to decide, okay. Then you have to initialize, the entire thing has to be initialized, because there should be something. So, these are basically iterative approaches. In CFD, you start with t equal to 0 and go to t equal to whatever time till you get the converged solution, right. Or if it is LES, then you till you start getting this statistically stationary solution, or the solution that you would expect at a given time accurate solution, right. But it has to start from something. At t equal to 0, you know, to specify what is my pressure, what is my density, what is my velocity, and so on and so forth, whatever the variables that we are using. Okay. These values usually do not change at the boundary, although there are time dependent boundary conditions also, but that is also you have to specify yourself at the boundaries here, okay, anywhere on the boundary, okay, you have to specify the value, or you have to apply, let us say, Nyman condition, okay, where it will be extrapolated depending on what kind of flow you have. Okay, and then finally, solution control, that means what is the CFL number that you want to use, for example, okay, that will give you the delta T. What is the convergence level that you want to go? Okay, if you are solving incompressible flow, then you have pressure Poisson equation. Okay, so there what is the tolerance level that you want to give? Okay, so all these things you can specify. There are things like you have to think about the under relaxation factor, over relaxation factor, and so many other parameters that you can think of. Okay, as you start using the any code or any solver, you would know what I'm talking about. Okay, so finally, once you have simulated and let us say you have got a solution, so let us say you are doing a RAND solution, then you will have some convergence. Okay, you start from some big value, okay, and then it will go to, let us say, 10 power -5 or -6, and then you say my solution has converged. So, this may be my momentum, this is my mass, this is my energy, and so on and so forth, right. So, at this point, when it has reached to this stage, you stop the solution, and then the next thing is to analyze the solution. So, how to analyze? There are several ways. First of all, to how does my flow look like, right? Is it making sense? Okay. For example, if you have a flow around an aerofoil, okay, so there will be stagnation point, okay, here, and so how will the pressure look like? Okay, are you getting this profile on the blade? So, first of all, to see whether the flow is making sense, okay, where the velocity should be accelerating, whether it is accelerating, are the streamlines okay, okay. If the Reynolds number is very low, or if the angular attack is 0 for this particular aerofoil, it should be for a symmetrical aerofoil, it should be symmetric. Are you getting the symmetric aerofoil? Is there any streamline which is penetrating? So, all those kind of things you need to see, and for that the most common tools are basically plotting the contours. You can make the velocity contour or the pressure contour, density contour, temperature contour. I mean, whatever variable that you have, you can use contour. That will give you the first picture of whether the simulation is making sense. You can also plot the streamlines, okay, and that will also give you some extra information. Let us say if there is a separation region, the streamlines will curl around there, and you can see, okay, this is the region where the separation is happening. Okay. Then, as I was saying, that let us say you want to plot the Cp here. Okay. Cp is the pressure coefficient. Okay. It's, you can think of as of now pressure. It's basically a non-dimensional pressure, P minus P infinity by half rho u square. So, you will basically talk about what is non-dimensionalization, but as of now you can think of this is a coefficient of pressure, okay, and let us say this is along my airfoil chord, okay, C by whatever the chord length that you have, or x by C actually, let me call it. This is x and this is C. So, how the pressure is varying? Are you getting, if you are expecting a lift, are you getting the lift? If it is 0 degree of attack, let us say it is symmetrical, then maybe both the pressure and suction side will nearly overlap. So, you will not get any lift. If you increase the angle of attack, you should get the lift. So accordingly the Cp curve should change. So that will give you a lot of information. You can also look at the velocity vectors. Okay. If there is a boundary layer, let us say this is an aerofoil and you are doing the simulation, viscous simulation, then the velocity should be 0 here. Okay, it will slowly increase and it should go like this, right. You should have boundary layer developing. If you have a separation, let us say here, then it will look like this. The velocity will be reverse here and then velocity go like this. Okay, then inflection point. So if you plot the velocity vector, you will get all the information. Then if it is a 3D flow, for example, you can also have the isosurfaces. You can have isosurfaces of vorticity, or you can have isosurfaces of Q criterion or several other criterion that will give you how the vertical field looks like. Okay. Yeah, I mean, like contour, you can use different isosurfaces of different flow variables that you have, whether the direct flow variable like rho, u, v, p, or you can have the derived flow variable like vorticity, okay, the Q criterion, lambda 2, several other things, any gradient you want to plot, okay, skin friction. So this we have already seen. So before you start a problem, you have to see what is the flow model that you are going to use. So based on the Mach number, okay, your flow can be incompressible or compressible. General thumb rule is if Mach number is greater than 0.3, okay, you should go with the compressible flow model. Okay. So you should use the compressible Navier-Stokes equations and all the necessary things that comes with this compressible Navier-Stokes equation. For example, you will have the ideal gas law or any gas law which relates the pressure to the density with the temperature. Okay, that is one thing. Secondly, you will have energy equation getting in, and then your viscosity may be varying. It is no longer a constant. Viscosity changes with temperature. There is a temperature change in compressible flow. So all these things you need to take care. Okay. Then based on what is the Reynolds number that you have, okay, so you can have the inviscid flow. Okay. So inviscid flow, which there is no viscosity. So the viscosity is 0. So that Re is basically almost infinity, you can think of. Okay. So viscosity is 0. So R equal to rho ul by mu. Okay. So if you have a dimensional solver, you can just say okay, viscosity 0. That means you are solving an inviscid problem or Euler problem. So equation will also change accordingly. Okay. All the viscous term that you have, you can explicitly remove that. Okay. Or if you have a viscous flow solver, you can set the viscosity to be 0. So that their influence is not coming. That means you will not have any boundary layer. Then you can have a laminar flow. Okay. You can also have the turbulent flow, and in between you can also have the transitional flow. Okay. So when you have the transitional and turbulent flows, things become very complicated. Okay. In fact, in hypersonic or supersonic flows, because of this interaction between the shock and boundary layer, even the laminar flows are not that easy. Okay. Because the shocks, so laminar flow will lead to the boundary layer, and then you have shocks which are coming because of the high Mach number, and they will interact with one another. Okay. And that will lead to separation, the shock strength will change, and so many things. Okay. So it is by itself a complicated problem, and then we are talking about turbulent flow. So turbulence is another thing which is I mean, as you know, it is one of the last unsolved problem, the turbulent flows, and because there is a Clay prize of $1 million US that if you can solve basically the turbulent flow in the closed form, you can basically claim that, right. So it is one of the most complicated problem. So what we do in our engineering approach, that we do not attempt to basically directly resolve the turbulence. What we do is something called RANS. Okay. So our governing equation itself changes. So this is Reynolds average Navier-Stokes. We will briefly look at it in the in next few lectures. Okay. And then you can so RANS is for turbulent, and then you have laminar, okay, and in between you have transitional. So you can tweak the RANS models little bit, so that the some region can be laminar, some region can be turbulent depending on the flow physics, and that will be the transitional model. Okay. And then as I spoke that the fluids may be Newtonian or non-Newtonian, and even non-Newtonian you have shear thinning, shear thickening, and many other things. Let us say you want to model a blood flow, there are different rheological model, okay, or you want to simulate fluids which are highly thick, or whose property change depending on how much pressure you apply. Okay. So those things need to be modeled, and they will go into the constitutive relations. So the tau that you have, okay, and in the Newtonian we say that tau equal to mu du by dy, okay, if you have a 1D flow like this. Okay. and similarly we have discussed the constitutive relation. So, depending on what fluid model using, this will change, the tau will change. Okay. Remember the conservations that we have, the mass, momentum, energy conservation, they will stay. Okay. But the constitutive model will change, it cannot violate the second law of thermodynamics or the Newton's law, right. So, as we discuss maybe in the 5th week that I mean these equations are derived from those basic principles, so they will not change, but what fluid you are using, accordingly you have to use this constitutive relation. And based on temporal nature, it can be steady or unsteady. Okay. In fact, even the flow is steady, that means it can achieve a steady state solution. You start with, you do not basically discard the d by dt term, you still keep the d by dt term, but you make sure that d by dt goes to 0. Okay. That is what we do in the range simulations. Okay. So, let me just quickly revise the equations that we have. So, this is for the compressible, we all know it, I will not belabor on it. Okay. So, we have mass, momentum and energy conservation. This is a vector equation. So, depending on how many number of dimensions you have in the flow, you will have 1D, 2D or 3D, and then to close this we will have the equation of state. This is an ideal one, but again as I told you that it may also change. You can have, let us say you want to do it for a flow which is different than an ideal gas, you will have to find an equation of state for that particular thing. Okay. And then we have this is the constitutive relation that I was talking about. This is for the Newtonian flow. Okay. Compressible, if it is incompressible, you know that del dot u goes to 0, it also gets simplified, and then we have energy diffusion and thermal conductivity which is coming in. Okay. And this is the approximation in the incompressible. Remember, no fluid is incompressible in nature, every fluid has got compressibility. Okay. But as we discussed earlier, perhaps that for example, air is more compressible than water, right. So, in certain regimes, okay, the compressibility does not matter and the fluid behaves almost like an incompressible flow. So, this assumption basically makes the physics much simpler. Okay. As you can see that constitutive relation, there will be mu here, okay, that will get simplified. This is the body force here, the mass conservation equation gets satisfied. I mean it just become a constant, there is no d by dt term here, it is just a constant. Okay. It is del dot u equal to 0, that is all it is. Okay. The rho you can take it out. Okay. This I have written in the form of Fm equal to ma. So, this is the force that you have and this is mass into acceleration, right, but you can also take the rho out and write in a different form. Okay. So, I mean this is the advantage of using incompressible, the things become simpler. Okay. The energy equation is there is no more energy equation here, but it also comes with certain costs. Okay. So, to absorb that, so I mean you just look at the Navier-Stokes equations. Okay. It does not have any independent equation for pressure. Okay. So, but the pressure affects the velocity, okay, the flow. I mean that is the most important quantity that affect the flow. The flow is actually driven by a certain pressure gradient, right. So, but for compressible flow, the good thing is that P is a thermodynamic pressure, that means P equal to rho RT, right. So, if you know the temperature and the density, you can get the pressure. Okay. And you have the density for the rho, you have d rho by dt, first equation you have, and the energy the temperature comes in the energy equation that you have. Okay. In fact, the energy equation can be written in many different form. Okay. So, you can have enthalpy equation, you can have the kinetic energy equation, you can have the kinetic energy plus so you can have rho E plus P. Okay. This is enthalpy. Okay. And the E has got 2-3 parts, one is that internal energy, another is called the kinetic energy. Okay. You can have the internal energy equation, you can have kinetic energy equation, you can have enthalpy equation. There are certain approximation, you can have Boussinesq equation also. So, I will not go into detail, but I am saying that the temperature can be obtained from this energy equation, and from this density and temperature you can calculate this P, which can be used in your momentum equation, right. So, that way you can calculate the pressure, which will satisfy everything. If you go to incompressible flows, okay, the P is a mechanical pressure. Okay, it should be flows, not the fluids. Okay, so, the P is a mechanical pressure, right. So, the mass conservation becomes a kinematic constant. So, you know this del dot u equal to 0. Okay. So, there is no dy dt term here. So, how do you time march? The only thing that you can time march in this equation that we have is this momentum equations. That is a dynamical equation. This is a constant. It must be satisfied at every iteration. At every iteration, when you take the gradient of del u by del x and del v by del y and let us say del u by del z and you add all of them, okay, it should come to 0, correct. So, it must be satisfied, but whatever velocity that you are getting from here, they should satisfy this, okay, but there is no separate equation for pressure or the I mean there is no separate equation for pressure here, right. So, how do we get that? So, we have no dynamic equation for either density or the pressure. So, then how to estimate pressure for incompressible flow? So, what we do? We use a trick. Okay. So, using this kinematic constant that we have del dot u equal to 0, okay, and the equation that we have, we will try to get another equation which is basically which relates the pressure to the velocity, right. So, that equation is called the pressure Poisson equation. Okay. So, what we do, we will take this, so this is in the vector form, okay. I have written it just to make it more simple. I have avoided the body force here. If you want, you can write rho f I, okay. So, yeah. So, you take the divergence of this, okay. So, that if you take the divergence of the entire equation like this, okay, what will happen? This is del dot u. So, this will go to 0, right. This is again you can the Laplacian and the divergence operator can be interchanged. So, this will become del square del dot u, okay. That will also go to 0, okay. And if it is conservative force, this will also go to 0. I mean, we are not discussing anyway the force here. So, now we have two terms, okay. One is del dot p, another is I mean there is another term which is del dot rho u u, right. So, this entire thing okay, I am seeing this entire thing as a force here. So, del square p equal to minus f, okay. So, this is called the pressure Poisson equation. This f is different from what f I was mentioning earlier, actually p should be capital, Poisson is the name of a person, okay. So, this is the pressure Poisson equation. So, what is it is doing is basically it is relating the pressure to the velocity, in fact in velocity gradient. So, if you are in 2D, you are basically you have del square p equal to minus rho u x square plus 2 u v x plus v y square, okay. In 3D you can accordingly you can basically derive this, right. So, what you do, so now we have got a relation which relates, and this has come by applying this del dot u equal to 0. So, you are not avoiding this kinematic constant, but you are intelligently using it in this form. Okay. So, how you can use it? So, you will do it in two step. Okay. So, first step is called a predictor, like we have been doing the predictor corrector approaches in the multi step method. Similarly, we will have something will predict and then we will correct it. Okay. So, first you solve the momentum equation with you take a guess for the pressure, and of course, the pressure will not be true, okay. It is a guess, and you get the provisional velocity field, okay. And when you get this velocity field, you will del dot u might not be 0, because you started with some pressure, right. Next is now you take this pressure Poisson equation, okay, to enforce the continuity, and that will update both the pressure and the velocity, right. So, first you started, you take a case for the pressure, solve the momentum, maybe x momentum, y momentum, z momentum, whatever that you have, you get the value of u v w, okay, and then you use this del square p is equal to minus f, okay. This is a Poisson equation, and f you can get from this velocity, you know the gradients, okay, and then you have del square p, and you have to satisfy this. So, this is a very costly operation, okay, and it corrects both the pressure and the velocity. Okay. So, this actually takes 80% 90% of the time in the computation in an incompressible solver. Okay, and there are several approaches to do that. There are schemes like simple schemes, okay, it is called semi implicit method for pressure linked equations, or the Peugeot schemes where you basically split the operator, the pressure implicit with splitting operators. So, these are used for pressure in the pressure based solvers. Okay, I will not say incompressible, because there are certain solvers which are pressure based, but they you can actually implement energy equations there, and you can also solve the compressor problem for that. These are called pressure based solver. So, if you look at fluent or even any solver, there will be explicit pressure based and density based solvers. Okay. For example, most of the solvers in open form are pressure based, but there are one or two density based. For example, rho central form is the density based solver. So, in the pressure based solver, pressure is a primary variable, okay, because using the pressure Poisson equation, and in the density based density is the primary variable, and you get this P is equal pressure as P equal to P equal rho r T. There is a coupling between pressure and velocity, which is basically segregated. Here it is fully coupled, the density equation, that is why we said that we can solve all the equations together, or it can be flux based. Okay. This is pressure Poisson, this is equation of state. The pressure based solvers are incompressible, or even low Mach number flows can be addressed using the pressure based solver. But density based solver is good when the flow is supersonic, hypersonic, you have SOX, SBLI and so on and so forth. Okay. The shock handling is moderate here, and density based excellent. Actually, the pressure based solvers are becoming advanced and better even for the shock based problems nowadays. The time step, you can employ larger time step, and that is why the pressure based solvers are popular. And density based, it is depends on the CFL number, and if it is explicit, the CFL number should be less than 1. Yeah, this is another thing. This is elliptic dominated, okay, because you have this pressure Poisson equation which is close to the elliptic equation. This is hyperbolic dominated, okay. And algorithms like simple piezo or the Riemann is solved, for the pressure based. For the density based, you can have the Riemann solvers like rho, HLL, HLLC, okay, or the central schemes with certain damping. Okay. So, modern CFD codes add compressible corrections to this pressure based solver. So, basically you add energy equation also in the pressure based solver, and also apply this equation of state. So, the applicability of the pressure based solvers are extended to the compressible flows also. Okay. So, it can treat both incompressible and compressible flows in the singular framework. Okay. So, some common solvers I want to just show. Let us say if you are using Fluent. So, the common solvers, if you are using pressure based solver, then you have like simple, simplex, piezo, and they are coupled, which are basically mostly used if the flow has got high Mach number. High Mach number means let us say Mach 0.7, 0.8, sometimes in the supersonic also. And then these are for like upwinding, first order, second order, quick and muscle. This we have discussed, that how do you increase the accuracy of the spatial discretization. If it is density based solver, then you have AUSM and AUSM plus, which are basically flux vector splitting, and then you have Riemann solver based approach, which are let us say the rho that we have discussed earlier, HLLC. Okay. And then you can there are certain versions of central schemes, but you require the dissipation, as we have discussed. The central schemes are basically unstable for convection dominated flows. Okay. So, that is why you use some dissipation there. Okay. And accuracy again it can be determined by first order, second order or muscle. If you go to, for example, open form, okay, so it is mainly pressure based solver. So, that is what I have discussed earlier. So, we have like simple form, piezo form, pimple form, rho pimple form, sonic form. So, these two can be used in compressible, but they are still pressure based solver. There are very few implementations of density based solver, although there are new solvers, basically user made solvers are coming up. So, rho central form is the default one in the open form. It uses central upwind, basically it is like the one we have discussed for in the central defensing, but with certain upwinding attached to that, otherwise it will not be stable. So, this is proposed by Kurganov and Tadmor. Okay. So, it does not have a Riemann solver kind of thing like rho or HLLC, as we have discussed earlier, but there are certain new implementations which are coming up, and that you can take a look. Okay. So, these are the solvers that we have. So, we will stop here, and in the next class we will see that how these equations can be solved using solvers, and also can we do non-dimensionalization. For example, in the flows what we have is Mach number and Reynolds number. Okay. So, how do we use these numbers to basically get the sense of what should be the density, pressure, velocity, etc. Okay. So, that is called a non-dimensionalization. It is a very important concept of CFD, and that we will look in the next class. Thank you very much.